Search in binary search tree. Searching in a binary search tree leverages its binary search property. What is this binary search property? We already learned that according to the binary search property, for any given node in the binary search tree, all the values that are present in its left subtree should be lesser than or equal to the value in parent, and all the values that are present in the right subtree should be greater than the value of the parent. This is the binary search property. Making use of this property, we are going to search for an element in this binary search tree. Let us understand how we are doing this. If this is your binary search tree, how will you start the search? For any search, first you have to identify the tree in which you want to search. How will you identify a tree? A tree is always identified by its root. So the search is also going to start from root. You'll start the search from root. Let us say you want to search for some element x. X is what you want to search. What will you do? You'll first come to the root and check whether the value in root is equal to x. If the value in root is equal to x, that means you already found the value, you are done with your search, you can come back. You can say, okay, I found the element at this particular position. If the value at root does not match with x, then what will you do? Then you have to check whether x is smaller than the value at the root or if x is larger than the value at the root. If x is smaller than the value at the root, then you know the value x, if present in this tree, will be present in the left subtree of the tree, because all the values in the right subtree of the tree we know are larger than the value of the root. We already know that x is having a value smaller than whatever is there in the root. So we have to go to the left subtree. What will you do? You will do the same process again. Again, you will check on this node whether it is equal to x. If it is, then you found it. If it is not, again you will continue the same procedure. You will check whether x is smaller or larger than this particular value. If it is smaller, you will go to the left subtree. If it is larger, you will go to right subtree. So we'll take some numbers and understand. We'll just dry run and see how to find it out. Then we'll do the pseudocode. Let us say this is your binary search tree. You have 50, then you have 21, 74, then you have 15, 32, 63 and 80. If this is your binary search tree, this is your BST. What do you want to search for? Let us say you want to search for 63. How are you going to search? You will come to the root and check whether it is equal to 63. Root is not equal to 63. What will you do? You will see whether 63 is smaller than the value at root or larger than the value at root. So here 63 is larger than 50. What will you do? You will go to the right subtree. In the right subtree, you reach 74. You will check whether 74 is equal to the value you are searching for. You are searching for 63. It is not equal. Then you will check whether the value you are searching for, that is 63, is it smaller than 74 or is it larger than 74? So it is smaller than 74. What will you do? You will go to the left side, because you know if this value is present, it will be present to the left side. So once you come to the left side, you will again check on this node whether the value is equal to 63. Yes, you found the value. So that's it. You can return this position. So this is how you search for an element. What will happen if the element is not there? Let us say instead of 63, you were searching for 65. So from 50, you will come right the same way you did for 63. From 74, you will come left because you are searching for 65 and it is lesser than 74. And at 63, you see that it is still not equal to 63. 65, whatever you are searching for is different. What will you do? You will check whether 65 is larger than 63 or smaller than 63. What did you find? 65 is larger, which means you have to go to the right side. When you go to the right side, what do you find? You reach null value. That is, there is no node present, so it will be null. So whenever you reach null while you are searching in a binary search tree, that means whatever be the value you are searching for, it is not present in this binary search tree. That is only when you hit null. So either you will find the element or you will hit a null, which means the value is not present in this tree at all. So this is how you do search in binary search tree. Let us write the pseudocode and understand how exactly it works. So let us write the pseudocode. We are going to search in BST. So let us name our function as BST search. And in the BST search, what should you have as input? You should have node and the value you are searching for. Let us say k is the value you are searching for. Node means initially whatever you will get will be root. I'm putting node here so that when we go inside the tree and go to different nodes, that makes sense. Other, you can put root as well, whatever is comfortable for you. So initially when you get the root, what all are you going to do? So whatever process we did practically now, we are going to convert it into pseudocode. What did we check first? First, we have to check whether the node is null, because if it is null, we have to return. So in the end, we saw the null condition when we were doing practically, but when we are writing the code, because we are going to write a recursive code, the same code is going to call itself again. Always you should put base condition first. So base condition will tell the code whether you have to exit or not. So the base condition is if node is null. If node is null, what will you do? If node is null, you can return. So you will return, let us say you will return null. So null is signifying that the value is not present. So whenever you hit null, that means the value is not present in this BST at all. What is the next thing you have to check? Next base condition is whenever you find the value of the key in any node, then also you can come back. So how will you do that? If node pointing key or node pointing data, whatever. So let us say node pointing data is the value of that node. If node pointing data equal to k is the key you are searching for. If it is equal, what can you do? You can return this node, because whichever node is holding the value, that is what you will return as a search result. So you will return node in case you found the value. Otherwise, if the node is not having the value, what will you do? You'll check whether the value k is larger than the node or if it is smaller than the node. So in case it is smaller, what will you do? If k is smaller than, lesser than node pointing data. So the value you are searching for is lesser than the value of the node. What will you do in this case? You want to go to the left subtree. In this case, we are writing a recursive algorithm. So you will return the same function you are going to call on the left subtree. So you will return BST search on left subtree. How will you call on left subtree? You will do node pointing left, node pointing left. And so here instead of node, you are going to pass node pointing left. That is the left child in the next iteration or recursion. So the reason why you are passing left is you want to recursively continue the same process on the left subtree and you are searching for the value k. What if this is not the case? What if k is not lesser? You know k is not equal, k is not lesser, so k will be greater than for sure. So it is the else case. Else. So what I'll do, I'll just write else if case. It should be else case only. I want you to clearly understand what is the condition. Else if k greater than node pointing data. If k is greater than node pointing data, that means the value if available will be available in the right subtree. So you have to return BST search. You want to call it recursively on the right subtree. How will you call on right subtree? Node pointing right. So when you call it on node pointing right with value k, it will try to search in the right subtree. So this is the recursive algorithm for binary search tree search. How do you search in a binary search tree? So as the name suggests, search is the most important operation in binary search tree. So how did you do search? In binary search tree search, first you check whether the node is null. If it is null, that means the value is not in the tree, you will return null. If the value is found, you will return the node in which you found the value. If it is not equal to the value in that node, you will check whether it is lesser. If the value you are searching for is lesser than the value in the node, in that case, you will recursively call it on the left subtree of the node. In case the value you are searching for is larger than the value in the node, you'll recursively call binary search tree search on the right subtree of the node. So this is what is binary search tree search algorithm. What is the time and space complexity of this algorithm? Time complexity, what will time complexity depend on? Depend on the height of the tree, because how are you searching? Each step you are going one step down, be it to left or right, you are moving one step down. So you will keep moving one step down in every call of recursion. So how much time will it take at max to find a node? Whatever be the maximum height possible for this tree, that is the worst case time complexity. So in binary search tree, we already discussed that in worst case height will go to order of n. So that is when it is a skewed tree. That is, if your tree is like this, all the nodes are directly down to each other, then height will be order of n if there are n nodes. So worst case time complexity is order of n for binary search tree search. Here, in case your tree is balanced, you can bring it down to order of log n. So we'll see how we do this when we learn about balanced binary search trees. But for binary search tree, if anyone asks you what is the time complexity, it is order of n. Next question is, what is the space complexity? So space complexity is here because of this recursive call. Otherwise, you're not using any extra space. But because of the recursive call, every recursive call will add new entry onto the stack. So it will take up stack memory and it will add to space complexity of this algorithm. So what will be the space complexity? Every time you call, you will add one new entry onto the stack. So again, one new entry. So whatever will be the height, that will be the number of calls. And the same number of times it will add recursive call onto the stack, which means space complexity will also be order of height. What is the worst case height? Height is n. In case, in the worst case, height can go to n. So with space complexity as well, the same rule applies. If you have a balanced tree, space complexity will also come down to order of log n. But in this case, it is order of n because of the height of the tree. One more thing is that this is a recursive algorithm that we used. So whenever we learn about trees, especially on trees topic, we generally always go for recursive algorithms because it makes sense, it is intuitive, and it is easier to read. While you are reading this, it's very intuitive and easier to read because you understand that, okay, at this point, you are going to recursively make the same call on left subtree. It makes a lot of sense. That is why we generally go for recursive algorithms. But instead, if you choose iterative algorithms, you can decrease the space complexity to order of 1. Because if you don't have this recursive call, you can decrease space complexity because you don't have to put anything onto the stack. It is because of recursion that stack is getting filled. So what we'll do is, in next lecture, we'll just see the recursive algorithm, how to write it, in case you want to bring this space complexity down to order of 1. So we'll see in the next lecture how to write a recursive algorithm for the same and bring space complexity down to order of 1.